Hello everyone, my name is Pipin Abram and in today's video we'll be talking about capacitors and capacitance. So let's get started. So capacitors are something which I'm sure all of you must have seen in your electrical appliances. So if you have a laptop or a phone or a computer CPU, if you have opened it up, you must have seen a motherboard, right, which is made up of silicon, right, silicon chip, right? So on that silicon chip, I'm sure you must have seen these kind of tiny and big capacitors. So all these, the images that you see, they all are different types of your capacitor. So what is the purpose of this capacitor on that motherboard? So basically, let's talk about what is the purpose of the capacitor. The purpose of your capacitor is they are basically an electrical device which are used to store charge or store electrical energy. So the purpose of your capacitor is to store electrical charge or electrical energy, right? And whenever that energy is required by the circuitry, it provided all at once, right? So that is the purpose of your capacitor. Is that a yes or no? So I'm sure the capacitors, are actually used in almost all of our electrical appliances. They are used in our smartphones. They are used in most of our, household appliances, right? They are used in our electrical vehicles. They are used for medical devices, right? So basically, I can say almost all our electrical appliances uses capacitor, right? I hope that is understandable, right? Great. So let's try to understand how these capacitors are made, right? So these capacitors are basically a system of two conductors when they are separated by insulator in between. So basically these capacitors are conductors, two conductors basically. You guys can see this is my conductor 1, this is my conductor 2, and when they are separated by insulator. Now you must be asking, sir, where is the insulator in between? So if there is air also, right, air, so I can see here there is air in between, right? So air also act as an insulator, right? So all you need to do is you need to have one conductor and the conductor, they must be separated by some distance. So in between there is actually an insulator called air, right? Air is actually an insulator. Is that a yes or no, right? So that is the construction here. So the first plate is always positively charged, and similarly the other plate, because of the induction effect, becomes negatively charged, right? Is that a yes or no? Okay, great. So you have to understand one thing here. The whatever charge that I give to my positive plate, I say that is the charge on my capacitor. That is how we just define it, right? So charge on your positive plate is taken to be the charge on the capacitor. Is that a yes or no? I hope that is understandable. Obviously this capacitor will have some area of cross section A1, this capacitor will have some other area of cross section, right? Obviously this capacitor will be at some potential V1, this not capacitor, actually this conductor will be at some potential V1, and obviously this conductor will also be at some potential V2, right? So when I say this conductor is at potential V1, that means all of the points that are inside there is at potential V1. Very similarly, all of the points that are inside here is at some potential V2. Is that a yes or no? So basically what is happening here, so capacitors are the devices which store charge, right? Now how they are going to store it? Now we know whenever we talk about a conductor, so when I give some charge to the conductor, we have studied from our previous videos, from our previous classes, that whatever charge that I give to the conductor, it is, it does not go inside, but it actually, stays at the surface of your capacitor. Is that a yes or no? Right? So you just give your charges and all the charges will be distributed at the, surface of your capacitor. So that's how you're basically charging your capacitor, right? So basically the capacitor is taking all of the charge and distributing it at the surface of the conductor. Is that a yes or no? Right? Okay, great. So that was all about your capacitor. Let's talk about what is capacitance. Now you have to understand the term capacitance, which is represented by the symbol C. It actually tells you how much charge your conductor can hold, right? So you are basically giving it some charge, you're giving your conductor some charge, giving it. So there must be a limit. You cannot just give it infinite number of charge, right? That is not how these things work, right? So there's a limit for your conductor to hold the charge, right? So that limit is something what we call as your capacitance of your capacitor. capacitance, that is the capacity of your capacitor to hold charge. I hope that is understandable, right? So it is the ability of the conductor to store charge. So your capacitance is basically a conductor. You have to understand that. Yes. So it is the ability of the conductor to store charge or energy. Now when I say energy, now how this, they are storing the energy. So let's go back to this picture here, right? So obviously this plate is positively charged, this plate is negatively charged. So because of this positive negative distribution, there will be an electric field. I hope you guys can understand, right? So this electric field is actually bounded. Can you guys see that? That electric field is actually bounded, right? So this bound electric field is actually the energy, that is, bound electric field will have some electrical energy, right? So this energy is what we call as your electrical energy. I hope you guys can understand that. Is that a yes or no? Right? Okay, great. So your capacitance is the ability of your capacitor to hold charge, right? Okay. So mathematically it is defined as the ratio of charge supplied to the conductor to change its potential produced in it, right? Obviously, so let's say I have this conductor, right? So let's say I'm giving it some charge. Let's say I'm giving it some Q0 charge, or let's say I'm giving it some Q charge, right? So obviously the moment I give it some Q charge, all of the Q charge will be distributed at the surface. Is that a yes or no, right? So because of the Q charge, the potential, it will gain some potential. Is that wrong? Let's say it gains some potential V, right? So your capacitance is defined by this ratio. How much charge that you're giving to the ratio of the change in its potential, right? I hope that is understandable. Is that a yes or no? So the ratio of charge, how much charge, this Q is charge provided to plus Q plate or plus Q conductor, and this V1 minus V2, V1 is the potential for your first conductor, V2 is the potential for your second conductor, right? So the change in potential produced in it, right? Change in potential produced in it. I hope that is answered. So your C is defined as Q upon V. Sometimes I write it as simply V, Q upon V. Is that a yes or no? I hope that is understandable. Yes? Great. So let's talk about the units here, right? So obviously charge as a unit of coulomb and potential as a unit of volt. So 1 coulomb upon 1 volt is what you call as a new unit, which is known as your 1 farad. You have to understand that 1 farad is a very huge capacitance. Now what I mean by 1 farad capacitance, it simply means 1 farad capacitance means 1 coulomb of charge and 1 volt in your denominator. That means you have a capacitor, right? So you are giving that capacitor 1 coulomb charge, right? You're giving your capacitor 1 coulomb charge, and because of that 1 coulomb charge, only 1 volt potential has been increased. I hope you guys can understand that. Is that a yes or no? So basically I have a very magical, conductor or a capacitor, right? So I'm providing it with 1 coulomb charge. Now we all know 1 coulomb is a huge charge, right? 1 coulomb is a huge charge of energy. 1 coulomb means in 1 coulomb charge there will be 6 into 10 to the power 18 electrons coming, right? Is that a yes or no, right? So you're providing it that much charge, and even after providing it that much charge, the potential of this conductor is only reduced by 1 volt. Is that a yes or no? So that is a very good capacitor we have here, right? So normally in normal cases what happens, the more charge that you give, the potential increases exponentially. Is that a yes or no? That is how normal cases go, right? The more charge you give to your conductor, the potential of the conductor automatically increases, right? Because of the increased potential, I cannot bring more and more charge because I feel the resistance from the charges which are already there at the conductor. I hope you guys can understand that, right? So 1 farad capacitance means I have provided 1 coulomb charge to my conductor or the capacitor, and only 1 volt potential has been increased in it, right? So like your 1 coulomb charge, your 1 farad is also a very large unit, right? So normally we use microfarad or picofarad or nanofarad, right? So these are the basic units that we use. We never use farad, right? Because farad is a huge unit. I hope that is understandable. Is that a yes or no? Now you have to understand your capacitors. There are different types of capacitors. One is your spherical capacitor, then we talk about parallel plate capacitor, then there is cylindrical capacitor. So there are like many types of your capacitors, right? So in our course we'll be talking about little bit of spherical capacitors, and mainly we will be talking about parallel plate capacitors, right? So in this video we'll be talking about cylindrical capacitors. We'll talk about we'll talk about the capacitance of a cylindrical capacitor, right? So that's all we'll discuss in this particular video, right? Okay, now one more important point that you have to understand here is that your C does not depend upon your Q and V. Although I have written here, I'm sure you must have seen, C is defined as Q upon V. This is how your capacitance is defined. But you have to understand, your C does not depend upon the charge or the potential change. Because why it does not depend? Because your C is actually a constant. C is the ability of the conductor to hold charge. Now that is something which is constant for any particular conductor. I hope you guys can understand that, right? So obviously if my conductor is big, it can hold charge more. Is that a yes or no? Yes, right? If my conductor is big, it can hold more and more charges, right? I hope you guys can understand. So basically your capacitance does not depend upon your charge or your potential. This is an important point which you have to understand, right? Very important. It does not depend upon Q and V. But we'll discuss in the later of the video, that in what all things your C depends. All right. Okay. So one thing you can clearly observe from here, or you can take away, is that your more the size of your capacitor, more the size of your conductor, more it has the ability to store charge, right? So it depends upon the dimension, right? I hope you guys can understand that. Yes, great. So let's do this problem. The problem says the figure shows voltage versus charge for a capacitor. So you have a capacitor and whose voltage versus charge characteristics are shown by a figure. The question is find capacitance. You have four options here: 40 microfarad, 400 microfarad, 30 microfarad, 4 microfarad. You can pause the video and can try it on, right? Okay, so you guys can see here, I know by definition the capacitance is defined as charge that is given to your conductor per voltage change in that, right? Is that a yes or no? Or I can actually write it in this form also: V is equals to Q upon C. Is that a yes or no? And I can see I have a straight line here, right? Can you guys see I have a straight line here? That means I can use my straight line equation, right? So what is your straight line equation? Yes, straight line equation is simply given as Y is equals to mx plus c, right? Where your m is the slope of your straight line, right? C is the intercept. Is that a yes or no? Intercept. Great. So I can compare. I have this equation here: V is equals to Q upon C, right? So I can write it: V is equals to 1 upon C multiplied by Q plus C plus 0 actually, right? So I can compare it: Y is equals to mx plus C. So I'm comparing it with your straight line equation, right? Okay, great. So by comparison, I get to know that along my y-axis I have my voltage. Yes, and that is true. Along my x-axis I have my charge. Is that a yes or no? Yes. Along my x-axis I have charge, right? I hope you guys can see. So your slope is actually 1 by c according to my equation, and I have the value of c to be 0. So the intercept is actually 0. That's why your graph is passing through the center. Is that a yes or no? Great. Now we also have studied that your slope is given as y2 minus y1 upon x2 minus x1. I'm sure you must have studied this in your coordinate geometry chapter, right? Slope is given as y2 minus y1 upon x2 minus x1. Is also given as tan of theta, right? So I cannot find out my theta here. I can actually find out my theta here, but I'm not bothered to find out the theta here, right? So I can see that I have 2 points here. This point is, this is your 410, right? And I have one more point here. I can take my origin to be 0, 0, right? So I can write it here. This 0, 0 is my x1, y1, and 400, 10, I'll write it my x2, y2. I hope that is understandable, right? Okay, so what I'm going to do here, so I'll just solve it here. Wherever I get space, I'll just solve it there, right? So okay, so your slope is actually 1 by 3, and that is given as y2 minus y1. So my y2 is, here my y2 is 10 minus 0 upon, yes, x2 minus x1. So what is my x2 here? x2 is actually my 400 minus 0, right? So I can see 1 upon c is equals to 10 upon 400, right? So this is cancelled out with this. So your c comes out to be 40 microfarad, right? I hope you guys can see that. I hope you guys understand, right? So here it is 40 microfarad, right? Is that a yes or no? Great. So let's talk about capacitance of a spherical capacitor, right? There's a trick to it. What is the trick here? We know that capacitor is defined as the system of two conductors when they are separated by some insulating material, right? Is that a yes or no? So basically here you have to understand, I have this spherical capacitor. Now I will assume my next capacitor is very far away, is at infinity. This is my assumption here, right? So I have my first capacitor, that is A plate. I have my B plate at infinity. Now why I am doing it? Because this has a potential 0. I want that this will have a potential 0 at infinity, right? So basically that is how I will talk about my one capacitor, right? Okay, great. So capacitance of a spherical capacitor. So I have this spherical capacitor, and let's say this has some radius r, right? And what I'm going to do here, I'm going to provide it some charge. Let's say I have given it some q charge, right? Positive q charge, I provided it, right? Okay, now you have to understand here, I have provided some positive q charge, and that positive q charge will be distributed at the surface, right? I hope you guys can understand, at the surface this positive q charge is being distributed, right? Great. Now let's try to understand here. I can say by definition, I can say by definition, I can say my capacitance for this spherical capacitor is written as whatever charge, that is the q charge I'm providing, and how much potential has been changed because of that q charge, right? So here I'll write it V1 minus V2, but you have to understand the value of my V2 is actually 0 because my second capacitor is at infinity. So I hope you guys can understand it now, right? So because of this, I want to make my second capacitor value to be 0. That's why I have written there V1 minus V2, and that's why my capacitor, you know, the second capacitor is at infinity. I hope you guys can understand that. Is that a yes or no? Great. So my C is equals to Q upon V1, right? C is equals to Q upon V1, right? Now you have to understand, at the surface, what is the potential here? V can be simply given as K, yes, Q charge I'm providing, divided by R. I hope you guys can understand this is something which we know it very well. Is that a yes or no? So what I'm going to do, I'll just substitute this value. This is Q upon K, Q upon R. So when I do the calculation, you will get Q upon 1 into R upon K Q, right? So Q and Q will cancel out, and I will get the 1 upon K can also be written as 4 pi epsilon naught, because the value of K is 1 upon 4 pi epsilon naught, right? So I can write it 4 pi epsilon naught multiplied by R. Is that a yes or no? Right? Because the value of K is 1 upon 4 pi epsilon naught, right? Because of this, I know I can put the values here, right, and get 4 pi epsilon naught times R. Now you have to understand here very nicely, the capacitance is written as 4 pi epsilon naught times your R. Now here you guys can see that my capacitance depends upon the dimension, because R, it depends upon R, right? It depends upon the dimensions of my conductor. I hope you guys can understand, right? Also, it depends upon epsilon naught. Epsilon naught is actually the medium term. Is that a yes or no? Right? It depends upon the medium also. You have to understand your capacitance does not depend upon the charge or the potential. It depends upon the dimension, how big your conductor is. The bigger the conductor, the more charge you can accommodate. I hope you guys can understand, right? It also depends upon the medium, right? So your capacitor, right now I can understand that my capacitor depends upon the dimension of my conductor. It also depends upon the medium at which I am keeping my conductor. I hope you guys can understand that. Is that a yes or no? Great. Now let's talk about the capacitance of Earth. Right now Earth is a big, I can assume my Earth to be a big sphere, and I can assume my Earth to be a conductor, right? Again, Earth, I can assume it is spherical, right? And I can assume that there is one more Earth which is like infinitely, infinite distance away from me, right? And the potential of that conductor is 0, right? I can do it like that. Is that a yes or no? Okay, let's try to find out what is the capacitance of your Earth, right? So I have this Earth here, and let's say the Earth has a radius r, right? Obviously we know the value of the radius of the Earth, right? What is the value of radius of Earth? Radius of Earth is 6400 kilometer. 6400 kilometer, and I can convert it into meter. This will be 6412123 meters, right? I hope you guys can understand, right? Now let's talk about the capacitance. I'm sure you must have done it by now. Capacitance of Earth can be given as 4 pi epsilon naught times of my r. So C is equals to 4 pi epsilon naught multiplied by 6412345 zeros, right? And C is equals to, I know the value of 1 upon 4 pi epsilon naught comes out to be 9 into 10 to the power 9. And what was the unit? You guys remember the unit? Unit was Newton. Yes, tell me. The unit was Newton meter square per coulomb square. I hope you guys can understand. Is that a yes or no? Okay. So if 1 upon 4 pi epsilon naught can be written as 9 into 10 to the power 9. So 4 pi epsilon naught can be written as 1 upon 9 into 10 to the power 9, right? And that is multiplied with 6412345 zeros, right? So when I calculate it, I'll get my value 711 into 10 to the power minus 6 farad. Or I can write it C is equals to 711 microfarad, right? Now you have to understand here, now what is the value of 711 microfarad? The value of 711 microfarad means C is equals to, I can write it 711 microcoulomb divided by 1 volt. Is that a yes or no? So you have to provide 711 microcoulomb charge so that Earth's potential is changed to 1 volt. Now you understand, it is very small as compared to 1 farad. Can you guys understand? It is very small. Although 711 microcoulomb is a good value of capacitance, but it is still very less as compared to 1 microfarad. Now let's try to understand how much should be the radius of my sphere so that I can get 1 farad capacitance. Let's try to find out, right? So the question is, I want 1 farad capacitance, right? What should be the radius of the sphere? Right, now this I can very nicely find out, right? Because capacitance is given as 4 pi epsilon naught times the r, right? Capacitance, I know I have to write it 1 farad, and this is 1 upon 9 into 10 to the power 9, and I do not know the value of the radius, which is something to have to find out, right? The value of radius will comes out to be 9 into 10 to the power 9 meter, right? So this much big, 9 into 10 to the power 9 meter, right? Or I can simply say r is equal to 9 into 10 to the power 6 kilometer. Is that yes or no? So this much big, dimensions I'll be needing. This is even bigger than the radius of the Earth. So I need a big sphere so that I can have 1 farad capacitance. I hope you guys can get the feel of it, right? So that is the problem with your spherical capacitors, right? So you cannot attain big values of capacitance with the help of your spherical capacitors, right? So it becomes practically impossible to make this large sphere so that I can gain big capacitance, right? So that's why in order to resolve these kind of issues, we moved on to parallel plate capacitor, which will be the topic of our next video. So stay tuned for that, right? So I hope you understood this video, right? So if you have any doubt, you can comment it down in the comment section, right? And I hope the video is understandable to you, and I hope all of you are doing good. Stay home.